Hello guys, I welcome you to my YouTube channel, and today I'm going to solve 9702 paper 1-1. It's May June 2022. These are multiple choice questions. Do not forget to subscribe, share the videos, invite many friends. You do not forget to also visit the topical past paper questions that have been solved in the previous videos. You just check through the video description to find the links to the question papers or to find the links to the questions for each topic. I have solved AS and A-level topical questions in the previous video, so do not forget to check them out. So without wasting time, I would like to take you to the question papers so that we solve the questions. So here is the 2022 May-June papers, and I'm solving 1-1. So my name is IBM. So always it's a good discipline not to leave any multiple choice question unanswered, because there are only 4 alternatives where you have to choose one, at least even if you don't understand the question. At the end of the exam, you should make sure that at least you have chosen or selected one alternative. At least you don't leave it blank. So which term represents a physical quantity? Of course, a physical quantity must have a magnitude and a unit. So a meter is just a unit. Percentage uncertainty has no unit. A quark flavor, this is just a quantity which has no unit. A spring constant could be newtons, it could be a number with a unit such as newtons per meter or newtons per centimeter, and so on and so forth. Remember from Hooke's law, force is equal to K times X, where K is the spring constant, which is going to be F over X. So it will be a number which has a unit as newtons per meter or newtons per centimeter, depending on the units for the extension. So the term which represents a physical quantity is going to be D. Which two units are identical when expressed in terms of SI base units? Identical. Let's check them. Let's start with joules per coulomb. Joules per coulomb is joules divided by coulomb. Remember, joule is a unit of work done, which can be force times distance. And force can be newtons times distance, which is in meters. Then divided by coulomb is a unit of charge. So joule is a unit for work done, which is force times distance. And of course, force can be newtons, but I can also write force as newtons, which is mass. Force is mass times acceleration, then times distance. So this could be kilogram for mass, meters per second squared for acceleration, then times meters. So this could be kilogram meters squared per second squared. Then we have coulomb is a unit for charge. This is a unit for charge, and charge is current times time. So the coulomb is going to be amperes, then times seconds. So it is ampere second. So if we divide, I'll divide kilogram meter squared per second squared divided by ampere seconds. So this gives me kilogram meter squared per ampere, then this becomes per second power minus 3, because there is an s at the bottom. When it goes up, it becomes minus 3. So these are not equivalent. Let's check B. Joules is kilogram meter squared per second squared, then times seconds. So this gives me kilogram. I'm on this one here. This gives me kilogram meter squared per second. And of course, it means this unit is the same as this. So the answer is going to be B, even if I don't check the rest. The value for the acceleration of free fall on Earth is given as 10 plus or minus 2 meters per second squared. Which statement is correct? The value is accurate but not precise. Of course, we know that the acceleration of free fall is supposed to be 9.81 meters per second squared. So when we say 10 plus or minus 2, that is the smallest could be 8 and the highest could be 12. Of course, the average value of these 8 and 12 is going to be approximately, let me check the average, 8 plus 12 divided by 2. It's approximately 10. 10 is very close to 9.81 to an accuracy of, to within, what is the difference? Let me first check the range. 10 minus 9.81. So the range is approximately 0.2. That is the range. So I can say that the value is going, this value here of 10.10 plus or minus 2 is going to be accurate because it is close to 9.81, but it is not going to be precise because the range is approximately 0.19 meters per second squared. That is a big range. So the value is accurate because it's very close to 9.81, but we cannot say it is precise because even when you look at this area here, it is a very big range. So the values, we can say the value is accurate but not precise. The value is both precise and accurate. That is not true. The value is neither precise, it's accurate because it is close to 9.81. The value is precise but not accurate. It's accurate. So the reason as to why I'm saying it is accurate, it is close to 9.81. But the reason as to why I'm saying it is not precise, first of all, this range of 2 meters per second is quite a big range. So we cannot say it is precise. If this was, because this is 9.81, if it was quoted as 10 point, say 00 plus or minus 0.02, we would say it is precise because there are more decimal places. But 2 is a very big number, so the range is relatively large. So we can say the value is accurate but not precise. Two cables are attached to a bracket and exert forces as shown. Okay, what are the magnitudes of the horizontal and vertical components of the resultant of the two forces? So in the horizontal, we have taking this to the horizontal, taking this one to the horizontal, they will all point to the right hand side. So we have 15 cos of 20 plus, this will be 6, because I'm using the angle 40, so it will be 6 sine 40. If I want to use cos, I will use 6 cos of 50. So this is in the horizontal pointing to the right hand side. And when I check with my calculator, I have 15 cos of 20 plus 6 sine of 40. That is 17.95 or approximately 18 newtons to the right hand side. So it means I have to choose from C and D. Then in the vertical, this point will point upwards, 15 will point upwards, and 6 will point vertical downwards. So I have to subtract them. So I will say 15 to the vertical to be 15. So I'm considering the vertical. So it will be 15 sine of 20 and it points upwards. So I'll subtract 6. Because I'm using 40 degrees, to be 6 cos of 40 downwards. I'm subtracting because it's downwards. So I have 15 sine of 20, then minus 6 cos of 40. So this gives me 0.534. 0.534. So the answer is going to be C because this is 0.534. So the answer is C. The curved line PQR is the velocity time graph for a car starting from rest. That means initial velocity is 0. What is the average acceleration of the car over the first 5 seconds? So remember, acceleration is going to be the gradient of a velocity time graph. The acceleration is the gradient of a velocity time graph. So where we see area, that one it means it will be wrong. Area of a triangle, that would be wrong. The gradient of the tangent at Q. So the answer is going to be C, the gradient of the straight line PQ, because we want average acceleration from 0 to 5 seconds. Why is Q wrong? When I find the tangent at this point here, I'm only finding the acceleration at Q. This one gives us acceleration at point Q only when I find a tangent here. But since we want the average, then it should be the gradient of the straight line PQ. So the answer is going to be C. A and B are wrong because area under the curve cannot be acceleration. Acceleration is the gradient. A ball is thrown horizontally with a speed of 10 meters per second above horizontal ground. The ball hits the ground after a time of 3 seconds. Air resistance is negligible. That means acceleration is constant. What is the speed of the ball just before it hits the ground? So I'll sketch this here. So let's say it is thrown from that level and this is the horizontal ground. So the ball is going to be thrown from this level here, and of course to follow such a path. When it hits the ground, it has a resultant velocity that we want to find, or resultant speed that we want to find, but has a speed in the vertical, which I'm going to call Vy. The speed in the horizontal Vx remains constant because there is no acceleration in the horizontal. So the speed in the horizontal, because it was thrown horizontally, the speed in the horizontal, even when it lands here, remains 10 meters per second. But the speed in the vertical increases because there's an acceleration in the vertical. So V in the y is going to be initial velocity in the y plus the acceleration in the vertical times t. So V in the y is going to be initial velocity in the y because it was thrown horizontally. U in the y is 0. Acceleration in the y is going to be 9.81, then times t, which is 3. So this gives me 9.81 times 3, which is 29.43 meters per second. So then I will find the resultant speed at the point of hitting the ground, which will be the square root of 10 squared plus 29.43 squared. So I find the square root. So the answer should be squared plus 10 squared. Then I find the root of the answer. So this is 31.1. 31.1. So the answer is going to be C. An object is moving along the ground in a straight line at a constant speed. Constant speed means acceleration should be 0. Which statement about the resultant force acting on the object is correct? If the acceleration is 0, it means the resultant force, which is MA, should also be 0. So the resultant force acting on the object is equal to 0. So I will just pick the answer D. Water flows out of a pipe and hits a wall. When the jet of the water hits the wall, its horizontal velocity V it has a horizontal velocity V and cross-sectional area A. So the horizontal velocity in hitting the wall is V. The density of the water is rho. The water does not rebound. So if it does not rebound, it means the horizontal velocity after, which letter should I use for this? Okay, I will just say V, fine, VF, that is V after, is going to be 0 in the horizontal. The horizontal velocity after is going to be 0. So what is the force exerted on the wall by the water? Okay, so I want you to recall from your concepts of force, density, and pressure. The mass is given by density times volume. And of course, we know that the volume is equal to the cross-sectional area times another distance or another length. But this time, we have the speed. The horizontal speed is v, and then let's say the time is going to be t. So this is going to be equal to cross-sectional area. Where there is L, I'm going to put there v times t, where small v is speed. And you also recall that the force is equal to change in momentum divided by time, or the rate of change of momentum. So the change in momentum is going to be the mass times change in velocity. So the velocity changes from v to 0 in the in the horizontal. Then we divide this by t. Small v is for velocity, capital V is for volume. Okay. Okay. So this means the resultant force is going to be M times small v, then divide by t. Okay, so I'll just substitute this. I'll just substitute for this. So this is going to be density times the volume, then times small v. Then I divide this by t. This is going to be, where there is capital V, I'm going to put AVT. So this is going to be density times AVT times V, divide this by T. So T cancels. This becomes density times A times V squared. So the answer is going to be automatically D. A projectile is launched at an angle above a horizontal ground and travels through the air. The projectile reaches its maximum height at position X. Assume that no upthrust acts on the projectile. Which diagram shows the directions of the forces, or forces acting on the projectile at point X? Now, at point X, the direction of motion of the particle is a tangent in that direction. So this is motion, not force. This is the direction of motion, which means the force which is acting, since it is in air, the force which is acting must be in the opposite direction, the force due to air resistance. So this is the force due to air resistance. Of course, there's another force which is the weight that acts vertically downwards. So this is the weight. So because the motion was to the right, the air resistance force is to the left, and the weight is vertical down. So these are the two forces acting. So this means our answer is automatically going to be B. Of course, I know many people will think the answer is A, but the answer is B because this arrow to the right is showing the direction of motion, yet air resistance acts in the opposite direction to motion. So my answer is going to be B. What is the statement of the principle of conservation of momentum? Of course, we know that for an isolated system of interacting bodies, total momentum always remains constant. And an isolated system is a system for which there is no resultant force. There is no resultant external force acting on the body. So we just look for an answer related to that. A force is equal to the rate of change of momentum of the body upon which it acts. That is Newton's second law. In a perfectly elastic collision, relative momentum of the object before impact is equal to the relative momentum after impact. This one does not exist. The momentum of an object is the product of the mass and the object. This statement is correct, but it's not the answer to that question. This is not the principle of momentum. Total momentum of a system of interacting bodies remains constant provided no resultant external force acts on the system. So if there is no resultant external force acting on the system, then it is an isolated system. So the answer is D. A horizontal wooden plank is pivoted at one end as shown. The plank has a mass of 100 kilograms, okay, and a length. So it means the weight is going to be, the force caused by this is going to be 100 times 9.81. That is the force. And the length of 10 meters. The center of gravity of the plank is a distance of 4 meters from the pivot. So this force, which I've just represented 100 times 9.81, acts at the center. What is the moment of the weight of the plank above the pivot? So moment, I will use tau for moment, is force times perpendicular distance from the pivot. So this will be 100 times 9.81, then times the perpendicular distance, which is 4 meters. So this is going to be 100 times 9.81 times 4, which gives us 3924. 3924 Newton meters, which makes our answer to be C. That is 4.0 times 10 to the power of 123. Okay, so the answer is what must an object be in equilibrium? Of course, in equilibrium, resultant force is 0, resultant moment or resultant torque should be 0. So this is not enough. An object would have no resultant force, but when a couple causes rotation, No resultant force, no resultant torque. So the answer is going to be B. No resultant force means there's translational equilibrium. No resultant torque means there is rotational equilibrium. It cannot move, it cannot rotate. So the answer is B. A uniform diving board is held by two fixed rods at point P and Q. A person stands at end R of the diving board as shown. The forces exerted by the rods on the board are vertical. Let's first see which forces are exerted here. So at P, the rod exerts a force vertically downwards. I'll call this one F at P. Then the rod at Q exerts a force upwards. I'll call this one F at Q. The weight of the man acts vertically downwards. I'll call this one F at R. And of course, it also has its weight. It is uniform. Its weight acts at the center. So let me look for the center here. W is going to be the weight of the body itself. The forces exerted by the rods on the board are vertical. The board remains in equilibrium. So it means resultant force is 0, resultant moment is 0. If the resultant force is to be 0, so I will say Fp plus W plus Fr should be equal to Fq. Okay. The person slowly moves towards point Q from end R. It remains in equilibrium as the person moves from point Q, towards point Q from R. So the person is moving in this direction. Which rod describes the changes to the magnitude of the forces exerted by the rods on board P? So let's start with force P. So I'm going to take a moment, I think I should take moments about point Q, moments about Q. So if I take moments about Q, it means I've eliminated FQ. But you'll notice that FP causes an anticlockwise moment about Q, so the perpendicular distance is going to be distance Q times P. Then this will be equal to Fp is anticlockwise, W is clockwise, Fr is clockwise. So this is going to be W times the perpendicular distance from Q. Perpendicular distance from Q, which is going to be a half. I want this distance here. Let me call it x for now. Okay, times x, which is the perpendicular distance, and x is constant. Then plus Fr times the perpendicular distance, which is going to be QR. Okay, but note that the person is moving from R towards Q. That means QR is decreasing, which makes this quantity smaller. And that means this is going to be smaller. If QR is decreasing, it means Fr times QR is smaller. So when we sum up, it is still smaller, which means Fp is going to be decreasing as QR decreases. So as QR decreases, Fp is decreasing. So Fp is decreasing. Fp must be decreasing. So we first ignore what increases. The force at P must be decreasing. Now, if the force at P is decreasing, go back to the first equation now. If F at P is decreasing, remember Fq is Fp plus W plus Fr. That means Fq is also going to be decreasing. If Fp decreases, because QR is decreasing, then it means since Fq is also depending on Fp, so it means Fq also decreases. So the force at Q also decreases, which makes the answer to be A. A solid block has sides of length L to L and 4L. The block is submerged in water of uniform density so that the faces with the largest area are horizontal. The upthrust acting on block U, on the block is U. The block is now rotated to a new position so that the faces with the smallest area are horizontal. The block remains fully submerged in the water. What is the upthrust acting on the block? Of course, the upthrust is still going to remain U. If you don't believe this, I can show you that it remains U. In this initial position, the upthrust U is going to be cross-sectional area times difference in pressure between the top and the bottom, which is the cross-sectional area times the density times G times change in height. That is difference in the change in pressure, which would be cross-sectional area is going to be 4L times 2L. That is the area over which the water is exerting a force. So that is the cross-sectional area, then times density, times then change in H is going to be simply L. So it means U is going to be 8L cubed density times G. Okay. Then let's check the second position. They have said it's now the smaller sides which are the smallest area are horizontal. So it means it is going to be like this. Something like this. It is now something like that, where this could be 2L, this is L, and this is 4L. So still it is the same thing. Let's check the upthrust here. We'll call it U2 is going to be the cross-sectional area, which is going to be 2L times L, then times the density, which is still the same, times G, then the H is 4L. So you notice that it still gives us 8L cubed times density times G, which is the same as U. So the upthrust still remains U, as long as it is fully submerged. If it was not fully submerged, then the vertical height could reduce. So the upthrust still remains U. In a large container in an oil refinery, 3 oils of different densities are mixed. No chemical activity occurs. The mixture consists of 1,200 kilograms of oil. Density is given as 1,100. 1,500 kilograms of oil. Density is 860. 4,000 kilograms of oil. Density is 910 kilograms. What is the density of the mixture? Okay, so we know that density of a mixture is equal to the total mass. Total mass divided by the total volume. So total mass, I'll sum up 1,200 plus 1,500 plus 4,000 over total volume. Total volume, remember volume is equal to density. Density is mass over volume, so volume is mass over the density. So for the oil, the first oil, I will have mass over density, which will be 1,200 divided by 1,100 plus the volume of the second one is going to be 1,500 divided by 860 plus the mass of the last one is going to be 4,000 divided by 910. Okay, so the sum here is 1,200 plus 1,500 plus 4,000. So this is 6,700. 1,200 divided by 1,100 plus 1,500 divided by 860 plus 4,000 divided by 910. So this is 7.23. 7.23. I'll just press my calculator and divide the answer. 6,700 divided by the answer, that is 926 approximate. 927 actually. This is 927. So the answer is going to be A. A box slides down a rough ramp. The change in gravitational potential energy of the box is 16 joules as it moves between positions x and y. The box has 24 joules of kinetic energy at x and 35 joules of kinetic energy at y. So it means the loss in kinetic energy is going to be equal to, not loss, the gain. Gain in kinetic energy is going to be 35 minus 24, which is going to be, I think this is 9 joules. Is it 9 joules or 11 joules? I think this is 11. So this is 11 joules. That is the gain in kinetic energy. But note that the gravitational potential energy of the box was 16. The loss in potential energy from x to y is 16. So it means the loss in gravitational potential energy has become the gain in kinetic energy, and some of it is being wasted as work done against friction. So how much work is done against friction? So the work done against friction is simply going to be 16 minus 11, which gives us 5 joules. So the answer is going to be A. Total energy supplied to an electric motor is E. Energy Q is wasted and the remaining energy does useful work. So which energy does useful work? So useful work is going to be equal to E minus what is wasted. That is the energy which does useful work. And we know that efficiency is equal to the useful work output. Useful is useful W, no. The useful work output or the useful energy output divided by the total energy input. So this is going to be the useful energy output is going to be E minus Q over total energy input, which is E. When I divide, it will be E over E minus Q over E. Everything divided by E, which is 1 minus Q divided by E. So the answer is going to be automatically C. Objects with different masses are placed on the horizontal surface of a table. The objects are then raised to different heights above the table. The gain in gravitational potential energy of each object is the same. The gain in gravitational potential energy of each object is the same. In other words, remember gravitational potential energy is equal to mgh. This quantity is constant here. They have different masses, of course, but g is constant. So it means m is inversely proportional to h because gravitational potential energy is a constant and acceleration of free fall is a constant. So m should be inversely proportional to h, or h is inversely proportional to m. That should not be one. It should not be a straight line. So I ignore this and this. That can't be a straight line. That's number one. Number two, as m increases, h must be decreasing. That means D is wrong because D is showing as m increases, h is also increasing. So the answer is automatically going to be A. H is inversely proportional to m. Two wires P and Q are made from the same metal and are hung vertically from a steel girder. Wire Q has half of the length and twice the diameter of P. So let's say length of P is L. The length of Q is going to be L over 2. Let's say the diameter of P is D. The diameter of Q is going to be twice D. Okay. Identical masses are attached to the bottom of each wire. So it means the force is going to be the same. force is the same for both wires. Both wires obey Hooke's law as they are stretched by the weight of the masses. Remember, they are made from the same metal. That means the Young modulus is also the same. E is the same. Young modulus is the same. Okay. What is the ratio extension of P, where P over extension of wire Q? So we know that Young modulus is stress, which is force over area, divided by strain, which is strain is extension of original length. And when we divide it, we get the reciprocal. So it is times original length over extension. Remember, the Young modulus is the same. So I'm going to just equate Young modulus for the first wire. The Young modulus for P should be the same as the Young modulus for Q. So the Young modulus for P will be the force. The original length is L. Cross-sectional area. Remember, area is equal to pi d squared divided by 4. So because I'm dividing, the 4 goes up. Young modulus becomes 4f L naught over pi d squared times E. So the 4 has gone up. Pi, the diameter for P is d, but squared. Extension for P, I'll call it EP, should be equal to Young modulus for Q, which is going to be 4. F was the same, but L was length over 2, L over 2, divided by pi, and D is twice. So I'll put 2D here, but it is squared, then times extension for Q. So some of these have already cancelled out. I'll use a different color for cancelling. So 4F pi. So when I simplify this, I have L divided by d squared EP is going to be, the 2 has gone down, and when I square 2d squared, it becomes 4d squared, and there is a 2 on top which goes down, so it becomes L divided by 2 times 4d squared, 2 times 4d squared times EQ. Okay, so L cancels out. I just cross multiply. I'm just cross multiplying, but leaving the EQ at the bottom. So I have 8 d squared L is equal to d squared times L, then times EP divided by EQ. So d squared L cancels out. I remain with EP over EQ equaling to 8, or 8 over 1. So the answer is going to be A. Which statement about elastic and plastic deformation must be correct? Remember, elastic, the material returns to its original length. Plastic, the material does not return to its original length. Okay, so let's see what is given here. Elastic deformation and plastic deformation are proportional to the applied force. Must be correct. Elastic deformation and plastic deformation are proportional to the applied force. I don't think that makes any sense, scientific sense. Elastic deformation and plastic deformation cause no change in volume. That is also not true because the wire stretches, cross-sectional area changes. Elastic deformation causes heating of the material, but plastic deformation does not. It is actually plastic deformation that would cause heating of the material. Elastic deformation is reversible. It can be changed or it can be removed. Plastic deformation is not. So the answer is going to be D. When a material undergoes elastic deformation, if the deforming force is removed, it can go back. So it is reversible. But plastic deformation, if the material undergoes plastic deformation, when the deforming force is removed, the material retains some length. So the answer is D. The graph shows the variation with the time of the displacement of a particle as a progressive wave passes. What are the frequency and amplitude? So for amplitude, I just look here. The amplitude is 5, which eliminates C and D. The amplitude should be 5. Then for frequency, frequency is equal to 1 over period, which is 1 over the period. I'll just take, I think this is the period, which is 10. So the period is 10, so I'll say 10 times 10 to the power of -9 because it is nanoseconds. So I have 1 divided by 10 exponent -9. So these are 1, 3, 6. That is 100. So this is 100 megahertz. So the answer is A, 100 megahertz. Yes, it is 100 megahertz. So the answer is A. The graph shows the variation of the displacement of an air particle with time as a speed wave passes through air. The intensity of the sound is halved. So intensity is halved. Of course, in your mind, you know that intensity is directly proportional to the amplitude squared. So intensity is directly proportional to amplitude squared, which means intensity should be equal to a constant times the amplitude squared. Okay, where the frequency remains constant, the four graphs below are drawn to the same scale as the graph above, which graph shows the displacement of the air particles. So the frequency remains the same. That means the number of cycles should be the same in the same time. Let's see. This is wrong because it's like the frequency has been increased. You can check. One cycle takes 1, 2, 3, 4 boxes. This one cycle is taking 2 boxes. So the frequency has been increased. We also check this one. B is automatically wrong because one cycle is taking 80 boxes, yet should take 4 boxes. So that is also wrong. Let's check C. C, the frequency is fine. 1, 2, 3, 4. 4 boxes for one cycle. 1, 2, 3, 4. D is also frequency-wise, it is fine. But we need to check now the amplitude. Intensity is directly proportional to amplitude squared. So for the first one, let the first one be this. Then when the intensity is halved, the second condition, it is going to be I over 2 should be equal to a constant times the new amplitude. I'll call it a 2, but this should be squared. So I'm going to combine the two equations. I'm dividing this equation divided by the first equation. So I have a2 squared divided by a squared should be equal to I over 2 divided by I, and I cancels. So I have that a 2 over a, and this is squared, should be equal to 1 over, it is 1 over 2. Then I find the square root. So a2 is going to be 1 over root of 2, then times a. 1 over root of 2 times a is the new amplitude. Let me just check. 1 divided by root 2. That is 0.707. So the new amplitude is 0.707 of the old amplitude. The first amplitude was 1, 2, 3, 4 boxes. So I'll multiply this by 4 times 4. So that is approximately close to 3 boxes. I would just say very close to 3 boxes. Because the first amplitude was 4 boxes. A is equal to 4 boxes. 1, 2, 3, 4. So it means the second amplitude should be very close to 3 boxes, which means this is wrong, and this is going to be very correct. 1, 2, approximately 3 boxes. Which statement is correct? Gases cannot transmit longitudinal waves. Of course, sound can travel through air, so that statement is not correct. Longitudinal sound waves cannot form stationary waves. That's not true. We can hear sound in a pipe. Those are stationary waves. Solids can transmit both transverse and longitudinal waves. Which statement is correct? Gases cannot transmit longitudinal waves. Longitudinal waves cannot form stationary waves. That is not correct. They can form. Solids can transmit both transverse waves and longitudinal waves. This statement is correct. We have seen sound going through solids. We have also seen light going through glass, which is solid, and so on and so forth. So that statement is correct. Transverse waves cannot pass through a vacuum. Of course, we know electromagnetic waves can go through a vacuum, so this statement is not correct. So the answer is C. A car is traveling at a constant velocity directly towards a man standing in the middle of the road. So it is towards. The frequency should be higher. The driver sounds the car's horn as a warning. The horn emits a sound wave of constant frequency. The frequency of the sound heard by the man is different from the frequency of the sound emitted by the horn. Which statement is correct? So this is Doppler what? Doppler effect. Which statement is correct? The frequency of the sound emitted by the horn is greater than the frequency of the sound heard by the man. Of course, because it's moving towards, the driver sounds the car's horn as a warning. The horn emits a sound wave of constant frequency. The velocity is constant and is moving towards. The frequency of the sound heard by the horn, emitted by the horn, is greater. No. The frequency observed is supposed to be greater than the frequency of the source. So this statement is not correct. The horn is the source and the observer is F naught. The frequency of the sound heard by the man depends on the distance between the car and the man. It depends on the speed and direction where it is moving, not the distance. The sound wave, so this statement is not correct. The sound waves continually accelerate as they move from the horn to the man, but this is moving at a constant speed, so this is not correct. So the answer is most likely going to be D. The wavelength of the sound heard by the man is less than the wavelength of the sound emitted by the horn. This statement is true. Remember, observed frequency is equal to V over V since it's moving towards, so this is going to be minus the speed of the source, then times the frequency of the source. Remember, V is constant, this is constant, then the speed of the source is also constant. So, because the observed frequency is going to be higher, then, and remember F is equal to V divided by the wavelength. Because the observed frequency is higher, it means the observed wavelength is going to be lower. So the wavelength of the sound heard by the man is less than the wavelength of the sound emitted by the horn. So the answer is going to be D. Which statement about electromagnetic waves is correct? A wave of wavelength 5 times 10 to the power of minus 6 is invisible to the human eye. Let's check. Reed's mother is visiting Uncle Xavier's garden. These are the electromagnetic waves. And this is the visible spectrum, which ranges from 7 times 10 to the power of negative 7 meters, that is red, to violet, which is 4 times 10 to the power of negative 7 meters. So negative 6 is on this side because wavelength is increasing this side, increasing wavelength to the left hand side. So negative 6 meters on the left hand side is beyond the visible spectrum, so these are going to be invisible. They can all travel at different speeds. No, they travel at the same speed. They cannot be polarized. Electromagnetic waves undergo polarization. They consist of vibrating atoms. That is very true. Which particles could be called photons? So the answer, no, not vibrating atoms. They consist of photons which are not vibrating atoms. So this is not correct. This is not correct. They travel at the same speed. That's not correct. So the answer is going to be A. A stationary wave is set up on a string that is stretched between two fixed points that are 48 centimeters apart. 48 centimeters apart. At one instant, the appearance of the string is shown. Okay. I will draw a horizontal line through this so that people can see that we have a half plus a half plus a half. That is 1.5 cycles. What is the wavelength of the stationary wave? So a half plus a half plus a half. So that is 1.5 of a cycle. 1.5 wavelength is equal to 48 centimeters. The length here is 48 centimeters. So this means we have 3 over 2 wavelength is equal to 48 centimeters. What is the wavelength? The wavelength is going to be 2 times 48 divided by 3. So we have 2 times 48 divided by 3, that is 32. So the wavelength is going to be 32 centimeters. So the answer is going to be B. A pipe closed at one end has a loudspeaker at the open end. For some frequencies of sound from the loudspeaker, a stationary sound wave is formed in the air within the pipe with an antinode at the open end of the pipe. Of course, there will be a node at the closed end. The length of the pipe is 0.85 meters. The speed of sound in air is 340 meters per second. Which frequency of sound from the loudspeaker would not produce a stationary wave? So I have this for a closed pipe, that will be the fundamental. Of course, we know for a closed pipe, the fundamental mode, of course, F naught is going to be V over wavelength. This is a quarter a cycle. The length L is equal to a quarter of a cycle. Because if it was a full cycle, we would have something like this. So if we are just seeing this part here, this is a quarter cycle. So this is going to be equal to V. So this means the wavelength here is going to be 4L. So it will be V over 4L. So for the fundamental mode, this V is going to be 340 divided by 4 times the length, which is 0.85. So what is the fundamental frequency? 340 divided by 4 times 0.85. So the fundamental frequency is 100 Hertz. But since this is a closed pipe, then the possible from Fn is equal to Nf naught. N must be equal to an odd number 1, 3, 5, 7, and so on and so forth. Only odd harmonics are present. So the first one is fundamental. F1 is 100. This is possible. 200 is possible. It said which frequency of sound from the loudspeaker would not be possible. Then no, 200 is not possible because it is 1, 3, 5, 7. So this is not possible. This is possible. This is possible. So the answer is going to be B. Not possible. Because if I put n equals to 1 to be 100, n equals 3 to be 300, n equals to 5 to be 500, then 700, and so on and so forth. Water waves of wavelength lambda are incident normally on an obstacle with a narrow gap. The width of the gap is equal to lambda. The waves from the gap emerge over an angle theta as shown. Okay, so you notice that it's almost that this distance here, even if you measure with a ruler, is approximately the same as this. So the diffraction is maximum. The gap is slowly widened. In other words, we are making the gap to be greater than the wavelength. Which changes, if any, occur to theta and to the wavelength of the emerging waves. Of course, the wavelength does not change. The wavelength does not change because it is depending on the source. So the wavelength remains the same, which means we eliminate C and D. The wavelength remains the same. But the gap has been increased. So what happens to theta? That is what happens to the angle of diffraction. So if we make the gap wider, instead of having such a bending, we may have something like this. We may have something like this. What is happening to theta? Of course, the angle of diffraction, or the angle, if I draw a new line here and here, it would mean that this angle here, the angle theta, is becoming smaller. So the angle decreases. So the answer is going to be A. Theta decreases, diffraction decreases, but the wavelength remains constant. Light of a single frequency passes through two narrow slits. There are two slits, that is a double slit. And whenever you see two narrow slits or double slits, the first thing to come into your mind is the double slit formula, AX divided by D. And produces an interference pattern on a screen some distance away. The interference fringes are very close together. They are very close together. Which change would increase the distance between the fringes? Of course, distance between the fringes is the X. So you notice that before you look at the answers, you notice that x is directly proportional to wavelength, x is directly proportional to d, x is inversely proportional to a. So increase the brightness of the light source. That does not affect x. Increase the distance between the slits and the screen. In other words, you are increasing d. It makes x to increase. So the answer is going to be automatically B. Increase the distance between the two slits. Of course, we don't have the distance between the two slits here. So it means it doesn't affect. Increase the frequency of the light used. When the frequency increases, the wavelength decreases. And remember, wavelength is directly proportional to x. So x decreases, so x would decrease. So this is also not correct. So the answer is B. Light of wavelength 5.4 times 10 to the power of minus 7 meters incident normal on a diffraction grating. The separation between adjacent lines in the grating is 2 times 10 to the power of minus 6 meters. Light that emerges from the grating falls on a semicircular screen as shown. Okay, so on a semicircular screen we expect a zero order maximum. Here then we expect n1, n2, n3, n1, n2, n3 and so on and so forth, above and below. The grating is at the center of the semicircle and the lines of the grating are vertical. How many bright dots are formed on the screen? So first of all, we find n on one side without including the central bright fringe. So we know that for a diffraction grating, n lambda is equal to d sine of theta. D sine theta. For n maximum, for maximum n, sine theta should be equal to 1. In other words, theta would be equal to 90 degrees. So it means n maximum should be equal to d, which is given as 2 times 10 to the power of minus 6 times sine of theta, which is 1, divided by the wavelength, which is 5.4 times 10 to the power of minus 7. So 2 exponent minus 6 divided by 5.4 exponent minus 7. So this is 3.7, but I'll round off to the smallest whole number there, which is going to be equal to 3. So n is 3 down, 3 up. Maximum 3 up, maximum 3 down. But there's also a central bright fringe. So we have 3 plus 1 plus 3. 3 up plus the central bright fringe plus 3 down, which gives us 7. So n is 7. Straight, please, you don't, I know this is 3.7, but it means it is supposed to be 3.7. We don't round off this to 4. It means the last order does not fit, so we can't round off to 4. We'll round off to the smallest number. A straight copper wire of diameter 0.42 times 10 to the power of minus 3 has a number density of free electrons. So this is small n, free electrons of 8.5 times 10 to the power of 28. In a given interval, a charge of 0.15 coulombs moves through the wire. What is the average displacement of free electrons along the wire in this time interval? Okay, so first of all, we know that current is equal to NQVA. That is current. And we also know that current is the rate of change, the rate of flow of charge current. So Q over T is going to be equal to NQV times A. Capital Q is total charge. So it means total charge Q is going to be equal to NQA times V times T. Of course, V times T is going to be the displacement. Velocity times time is going to be the displacement. So Q is going to be NQA times the displacement. I'll use capital S for displacement. So what is the average displacement of the free electrons along the wire in this time interval? So the displacement S is going to be equal to Q, where Q is 0.15 coulombs, divided by N. N is 8.5 times 10 to the power of 28 times Q. Q is, these are electrons, so Q is the charge of one electron, which is 1.6 times 10 to the power of minus 19, then times area. They gave us the diameter. The area is going to be pi d squared over 4. So the 4 goes up, so I'll say times 4. And in the denominator I have pi times d, which is 0.42 times 10 to the power of minus 3, and this is squared. Okay, so I'll just press my calculator. I'll start from the denominator because it's kind of weird. 8.5 exponent 28 times 1.6 exponent minus 19 times pi times 0.42 exponent minus 3, but this should be squared. Then I'll get the numerator, which is 0.15 times 4 divided by the answer. So I'm getting 7.9, which is approximately 8.0 times 10 to the power of minus 5. So the displacement is 7.96 times 10 to the power of minus 5 meters. So the answer is going to be C. Note that when I substitute for area in this formula here, I said S is equal to Q divided by N small q small a. The area is pi d squared over 4, so the 4 goes up, so it becomes 4q divided by n small q pi d squared. This is what I've done in my substitution. What is the definition of the potential difference across a component? So we know that V is equal to E over Q, where E is the work done, or the energy converted from electrical per unit charge. So the answer here is going to be B, the energy transfer to the component per unit charge. It is converted from electrical to thermal per unit charge, so that is going to be B. The IV characteristic of a semiconductor diode is shown here. Which statement can be deduced from the graph? Above a certain positive potential difference, the diode obeys Ohm's law. There is, of course, here Ohm's law. Ohm's law is only obeyed when the graph goes through the origin, so this is not correct, and it is a straight line. Current is directly proportional to the potential difference when the current in the diode is in one direction. That is not true. The diode has zero resistance when the current in the diode is in one direction. Resistance is not zero in one direction. This side, I don't think this gives us zero. There's a current here. This side is not zero because there's a current. But the current is not, of course, zero resistance means there's maximum current. So this is not going to be true. The resistance of the diode depends upon the potential difference across it. This is going to be very true. After a certain value, then the resistance starts decreasing. So the answer is going to be D. The resistance of the diode depends upon the potential difference across it. A wire has a resistance 30 ohms. A second wire is made from the same material, so that means they have the same resistivity. Has the same mass, the mass is the same, and is 3 times as long as the first wire. So if the first wire is L, the second wire has length 3L. What is the resistance of the second wire? Okay. So to begin with, we know that mass is going to be density. Because I'm using rho for resistivity, I'll use D for density. Mass is density times volume, which is going to be density times cross-section area times L, which means area can be mass divided by density, then times L, that is area. But we also know that resistance is equal to rho L over the area, which would be rho times L divided by the area, which is M times D times L. So dl goes up, it becomes rho L squared times D, then divide by M. Okay, so now I'm going to substitute. For the first wire, let's say for the first wire, the wire has resistance 30, so I'll say 30 equals to rho L squared times the density divided by the mass. Because from the same material, resistivity is the same and the density is also the same. Then for the second wire, its resistance is not known, resistivity is the same, but the length is twice L. The density is the same because they are from the same material divided by the mass. The mass is also the same. So when you compare the two equations, or when you divide, you have that R divided by 30 is equal to, remember this was squared, is equal to rho into 4L squared times D over M, then again divide by rho L squared times D over M. So M cancels, L squared cancels, D cancels, rho cancels. I'm only remaining with 4. So R over 30 is equal to 4. So what does that mean? R is equal to 4 times 30. Is it 4 times 30? Oh, this was 3L, not 2L, 3L, which makes this one 9. So this is 9, not 4, because it was 3L. So when you square it, it becomes 9. So this is going to be 9 times 30, which is 270. So it means our answer is going to be D. Okay, sorry for that. If I make a mistake, just know it's because I solve these questions naturally, so I must make some few mistakes. A cell has internal resistance R and electromotive force E. The cell is connected in series with an ammeter and a variable resistor of resistance R. When R is 10 ohms, the ammeter reads 0.3. And when R is 5 ohms, the ammeter reads 0.4. So I'm just going to come up with two equations. We know that the EMF is equal to the terminal PD time plus the PD across the internal resistance, which is going to be I times capital R plus I times small r. So when R is 10, we have the EMF is E is equal to I into 10 plus internal resistance R. So E is equal to 0.3 into 10 plus R. And then the second one, E is going to be the current is 0.4 into 5 plus R. So I'm just going to solve these two equations. I just equate them. So when I equate the two equations, I have that 0.3 times 10, which is 3, plus 0.3 R should be equal to 0.4 times 5, which is 2, plus 0.4 R. I've just equated the two equations after opening the brackets. So when I subtract, when I collect like terms, I have 0.4 minus 0.3, which is 0.1 R, equals to 3 minus 2, which is 1. Which means R is going to be equal to 10 ohms, that is small r. Then E is going to be using the first equation, using this one, is going to be 0.3 into 10 plus 10, which gives you 20 times 0.3, which is 6 volts. So my answer is going to be D. The sum of the currents entering a junction in an electric electrical circuit is always equal to the sum of the currents leaving the junction. That is Kirchhoff's first law. And the first law is conservation of charge. So why is this? Why is this? It is a consequence of the conservation of charge. So the answer is A. Total charges into a junction should be equal to total charges leaving the junction. That is Kirchhoff's first law. Remember, the second law is conservation of energy. So conservation of energy is the sum of the PDs equals the sum of the EMFs. In the circuits shown, the temperature remains constant. The temperature remains constant. That means the resistance of the thermistor does not change. I'll say R of the thermistor remains constant. In which circuit does the potential difference V increase with increasing light intensity? Of course, we shall not consider A because in A there is no what? There is no LDR. In A there is no LDR, so light intensity is not affecting anything. There is no LDR here. This is a thermistor. Then we look at B, C, and D. In B, the PD is measured across the LDR. So the light intensity has been increased, which means the resistance of the LDR decreases because they are inversely proportional, which means the PD across the LDR must decrease because the PD is equal to I times R. Because R has decreased, the PD should decrease. So B is also out. We want V to increase. C. Of course, C is almost the same as B because the thermistor, the temperature is remaining constant, so this is not affecting anything. And V is measured across the LDR. Light intensity increases, resistance of the LDR decreases, so the PD we are measuring across the LDR decreases, so this is out, which means the answer is going to be D. If we measure PD across the thermistor, here when the light intensity increases, the resistance of the LDR decreases, the PD across the LDR decreases. But remember, the PD is measured across the thermistor, which means the PD across the thermistor increases. So it means V increases because V is measured across the thermistor, not across the LDR. If it decreases across the LDR, it should increase across the thermistor by conservation of energy because the sum of the two should be equal to the EMF. So the answer is going to be D. Carbon-14 decays into nitrogen by emitting beta minus. Which statement explains why the beta minus particles are emitted in a range of different kinetic energies? Let's just see what happens when a neutron changes to a proton. This is accompanied by beta. This is to form beta minus. Of course, beta minus is accompanied by an antineutrino. An electron is accompanied by an antiparticle. So the energy is going to go to the nitrogen nucleus. Some of the energy goes to the beta minus particle and some of the energy goes to the antineutrino. So the energy is being shared. So the answer rotates around sharing the energy. So the answer is going to be D. The energy released in the decay process is shared between the nitrogen nucleus, the beta particle, and an antineutrino. So the answer is D. A nucleus of radioactive element emits an alpha particle, then a beta minus particle, and then another beta minus particle. Which statement describes the final element that it produces? Let's first check. Let's say it is X, nucleon number A, proton number Z. It is going to give us Y, nucleon number P, and proton number Q, plus an alpha particle, which is alpha 42, plus a beta minus particle, which is beta 0 minus 1, plus another beta minus particle, which is beta 0 minus 1. Okay, let's check the values of P and Q. So P is going to be equal to A minus 4, and Q is going to be equal to Z minus 2 plus negative 1 plus negative 1, which is the same as, this was Z, which is the same as Z, which is the same as Z. So in other words, Q is equal to Z. Most likely this is what is formed is an isotope. It is a different element of higher proton number. Proton number is Z, is the same as before. It is a different element with a lower nuclear number than the original. It is a different element. It is not a different element because the proton number is the same. It is an isotope of the original. The answer is going to be C. It is an isotope of the original. And lastly, because the proton number is the same, we saw that Q was the same as Z as before, so it is an isotope. How many hadrons, baryons, and mesons are there in the nucleus of beryllium? So there are 4 protons plus 9 minus 5, 9 minus 4, those are 5 neutrons. So these ones are baryons. Protons and neutrons are baryons, so 9 baryons. They are also hadrons, so we have 9 hadrons. Protons and neutrons are also hadrons. Then there is no meson here. So 9 baryons, 9 hadrons. So we eliminate A and B because the number of baryons is the same. So it means that our answer is automatically C without even wasting time. 9 hadrons, 9 baryons. Protons and neutrons are baryons. They are also hadrons. So the answer is C. Okay, I think that should be the end of this paper, and see you in the next paper. Bye bye.